Hello everyone. So today we are going to talk about Euler circuits and Euler paths. So Euler circuit and Euler paths are quite intricately connected to the birth of graph theory. So there was a town called Königsberg and there was a river flowing through it, and the town was divided into 4 regions by the branches of the river. There were 7 bridges connected to these regions, and people wondered that is it possible to start at some location, some region, travel across the bridges exactly once and return to the same starting point. And the famous mathematician Leonhard Euler solved this problem by converting this or modeling this problem in a graph theory problem and solving it. So that graph will see that you can do that. The answer is yes. So that's the problem of Euler circuits or Euler paths. So let's see the mathematical definition of it. An Euler circuit in a graph G is a circuit that visits each edge exactly once. So we know it's a circuit, and a circuit means it's a circular path. Means it's a path, so it goes through all these edges exactly once, and the starting point and the finishing point is the same. That means you end up where you started from. And an Euler path is just a path that visits each edge exactly once. So let's see some examples. Which of these graphs have Euler circuit and which one doesn't? So this is a graph G1. It has 5 vertices and 6 edges, and just by looking at it we want to know, does this graph has an Euler circuit or not? The answer is yes. Well, you can start from here. You can go this way, this way, this way, and come back here. So if this vertex is your starting point, you can get through all the edges exactly once and return where you started from. So if you are asking, does this graph G1 has Euler circuit? The answer is yes. And let's look at this graph now, G2. It has 6 vertices, 1, 2, 3, 4, 5, 6, and this many edges, and we are asking, does this graph has an Euler circuit or not? If you do this way, you start from here, go this way, this one, then this one, you're stuck, so can't do that. This way, stuck because you already explored this edge, can't do that. If you return here, these 3 edges are unexplored, so can't do that. So the answer is no. So this graph has Euler circuit. This graph doesn't have any Euler circuit. Do we have a mathematical formula? Mathematically, can we solve it without trying? Without trying all these different paths and circuits, can we look at a graph and tell whether it has Euler circuit or not, it has Euler path or not? Can we do that? Yes. So that's the next theorem. A graph G has an Euler circuit if and only if each of its vertices has even degree. So the answer is pretty simple. You take a look at the graph, you figure out the degrees of each vertex, and if all of them are even, that means all the vertices have even degree, then the graph has Euler circuit. Otherwise it doesn't. So check with the examples here. So what's the degree of this vertex? It's 2, 2, 4, 2 and 2. So all of these vertices have even degree, and that's why we have the circuit. Let's take a look here. 3, 3, 4, 4, 4 and 2. These 4 vertices have even degree, but these 2 have odd degree, so they do not have all even degree. That's why it doesn't have an Euler circuit. So let's try to prove this theorem mathematically. So this theorem has an if and only if statement. So there is an if part, there is an only if part. So let's do one part first. If G has an Euler circuit, then all vertices have even degree. How do we prove that? I'll just show you the simple construction. Let's say so let's see the starting vertex. The starting vertex, which is same as the ending vertex, is A. So given any vertex, it is either A or it's some other vertex that is not A. There are two types of these vertices in this graph. Since we have an Euler circuit in this graph, so let's talk about the A. So if we have an Euler circuit, you start from here and you get out to some vertex. So this is the first time. So first time you start from A and you get out to another vertex. Then you go round about, do something, you come back. Now all the edges are visited exactly one. The vertices can be visited more than once. So you go here, you get out another time, back here. You can get out one more time, once more, as many times as the circuit permits you, but there will be one last time. Now you see that each time you get out using an edge, there is another edge using which you get in. So in, so out, in, out, in, out, in. So each time you get out, you have one getting in. So even degree. Similarly for V not equal to A, so for all the other vertices, so you are traveling across the Euler circuit. So you get into V, you get out. Then you travel through the circuit, you may get in once more, you get out, because you are not stopping at this vertex, because A is the only vertex where you are finishing. So if you get into A, so if you get into V, you are always getting out of V. So in, out, in, out, in, out once more. That's why even degree. So if you have an Euler circuit for every vertex, this is true. You go in that vertex and get out of that vertex. So there are always two edges whenever you are going through that vertex. So 2, 4, 6, that type. So the graph will always have vertices with even degree. So if G has an Euler circuit, then all vertices have even degree. Now the second part of the proof. If all vertices have even degree, then G has an Euler circuit. So all the vertices, we have a graph G where all the vertices have even degree, and we are trying to prove that G has an Euler circuit. How to prove that? Given this graph, if we can construct the Euler circuit using a process or an algorithm, then we know that it will always have an Euler circuit. So given a graph with all even degree vertices, how can we construct the Euler circuit? We'll do the sketch of this process. The detailed process is in the book, you can read on there. So start with any vertex, any arbitrary vertex. So just pick a vertex and start from there. Second, traverse using an unexplored or untraversed edge. So start from a vertex and pick an edge that you haven't traversed through and go there. Continue that as long as you can. So keep finding an unexplored edge and go to the next vertex. Keep doing that. If you're asking, how can you guarantee this? How do I know that standing on a vertex I can always find an edge which is unexplored, through which I have not gone through? Well, you can always do that because every vertex has even degree, so that makes it possible. If you can get into a vertex, if you can get into a vertex V, then you can always get out of it using an unexplored edge. So you can always do that. So that's the end of the process. So what was the process of constructing the Euler circuit? Let's start from any arbitrary vertex and traverse using an unexplored edge. Start from a vertex using an unexplored edge, go to a different vertex. Continue doing that as long as you can. So when will you stop? You will eventually stop at the starting vertex. You will always be able to get out of all the other vertices, and you will see that when you stop, you will actually stop at the starting vertex and all the edges have been explored, and the circuit that you created is the Euler circuit. So given a graph with all the vertices of even degree, you can construct an Euler circuit. So the graph always has Euler circuit. And that concludes our proof that if a graph has an Euler circuit, then it has all its vertices even degree, and if a graph has all vertices of even degree, then it has an Euler circuit. And that's the very simple test of Euler circuit in a graph. Next is Euler path. That's also simple. Next, we talk about Hamilton circuit and Hamilton path. So Euler both circuit and path was with exploring every edge. In case of Hamilton, both circuit and path, it's about exploring every vertex. So remember this difference. Hamilton is about exploring every vertex. Euler is about exploring every edge. So Hamilton circuit it's a circuit that visits each vertex exactly once, and a Hamilton path is a path that visits each vertex exactly once. So let's see some examples. Do these graphs have Hamilton circuit, Hamilton path? Let's start with G1. So G1 has 5 vertices, A, B, C, D, E, this many edges. Does it have a Hamilton circuit? Can you go through all the vertices exactly once? We don't care about all the edges or not. The answer is yes. For example, you start from A, B, C, D, E, A. Hamilton path? Yes. A, B, C, D, E. So G1 has both Hamilton circuit and Hamilton path. Good. Let's try with G2. Does G2 have Hamilton circuit? The answer is no. Why not? If you start from here, you go A, B, C, D, cannot go back to A. So no matter what you do, this edge will be your problem. This is the reason. Because any circuit has to have this edge AB twice. Now that's not possible. Then we won't be visiting the vertices A and B exactly once. So that's the reason. Does it have a Hamilton path? Well, yes. For example, A, B, C, D. So G2 does not have Hamilton circuit, but it does have a Hamilton path. Let's see G3. Does it have a Hamilton circuit? No. For the same reason. This edge. If you have to have a circuit, then you have to explore this edge twice, and then you will be exploring both A and B twice. So no. Hamilton path? No. Because any path containing all vertices must have the edges A, B, C, D, E, F more than once. And if you have these edges more than once, then you are going through the vertices more than once. Then that's not a Hamilton path or a circuit. So that's the reason. Now you are asking, okay, so given a graph, by looking at it, can I tell whether it has an Hamilton circuit or not, it has an Hamilton path or not? Do we have a similar theorem, a similar checklist, like the Euler circuit, Euler path? We have a theorem, a checklist. Do we have something similar for Hamilton? Sadly, the answer is no. We do not have a small checklist to figure out whether the graph has a Hamilton path or not, Hamilton circuit or not. So all you can do is, given a graph, try and then draw a conclusion. Few things that you should look into it while looking for whether the graph has an Hamilton path or not, Hamilton circuit or not, is the conditions are the conditions for the existence of Hamilton circuit. Is, for example, a graph with a vertex of degree 1 cannot have a Hamilton circuit. Look at the example G2. This graph has this vertex A with degree 1. That's why no Hamilton circuit. This graph G3 has a vertex A, has a vertex D and also F with degree 1. That's why no Hamilton circuit. Moreover, if a vertex in the graph has degree 2, then both edges that are incident with the vertex must be part of any Hamilton circuit. So these are some small checks to figure out whether a graph has Hamilton circuits or not. But this list is not complete. So just by checking these things, you cannot conclude correctly. That's it.